Okay, so today we're going to go ahead and talk about how to solve like a pulley system, which is a classic physics example. So the cool thing about pulleys is they just change the direction of the applied force. And if we have, let's say, what we assume to be a frictionless pulley, then that'll just mean that tension in the rope will stay the same throughout. So this right here is supposed to be a little pulley right here, and then this rope right here connects the 8 and 10 kilograms objects together. So we'll assume that we have a frictionless pulley so that the tension is constant throughout. Cool. So, okay, let's think about it. So what could make sense for the acceleration of the system? And I want you to think about what number the acceleration of the system could not be above. So go ahead and think about that, and then you can check back into the video. Okay, so we know the pulley system is going to slow things down so that things will not be in free fall. So the biggest acceleration can be is 10 meters per second squared in magnitude, because that's free fall, and the smallest is 0 meters per second squared, because that just means something's moving at constant speed or something is at rest. Cool. So again, first thing that we always do when we're solving a fun little physics problem is we draw a free body diagram. So I'm going to go ahead and draw that. So we have Fn, we have force of gravity, we have tension right here, we have tension in this rope, and we have force of gravity, 100 newtons here. This Fg, I should call that 80 newtons. Okay, and it talks about friction. Okay, so there has to be friction pulling this back to the left. Okay, so great. So now let's go ahead and think about it. And you know what, I should have just read the problem at the beginning, but we'll read it now. So in the system below, the block of mass 8 kilograms is on a rough horizontal table. Cool, so we included friction. The string that attaches it to the block of mass 10 kilograms passes over a frictionless pulley of negligible mass. The coefficient of friction between the 8 kilogram block and the table is 0.2. So I'll put over here mu is 0.2. Find the acceleration of the system and then find the tension in the string. Okay. I'm just going to go ahead, just for fun, label if I know a couple other forces. Okay, so it's accelerating. So I know tension and gravity should not equal the same thing. Okay, so let's see. We have Fg is 80 newtons here. I know this 8 kilogram is not accelerating in the y, so Fn has to be 80 newtons. Let's go ahead and calculate Ff. So I know Ff is going to be mu times Fn, and the coefficient is what? 0.2 times Fn is 80, so Ff is 16 newtons. Cool. Cool, so one thing I can think about, like, okay, if it's accelerating to the right, I know this tension force has to be bigger than 16 newtons, so that's just good to keep in mind when we're solving. Okay, so now what we need to do is, after we draw a free body diagram, draw a coordinate system. Okay, so for a coordinate system, I'm going to say the direction that the system moves is considered to be the positive direction, and the direction of the rope is the x direction. Okay, so this thing is accelerating downwards, so we're going to call that direction the positive direction. And this, any force that is along the line of the rope is considered the x direction. So again, like some people like opening it up so that if you think of this as like 8 kilograms, we have tension here, we have friction pulling this way, we have Fn, we have Fg, and that's connected to the pulley, which is then connected to what we have Fg, which is 100 newtons, and we have tension pulling back this way. So people kind of just like essentially move this up, and we're like opening up the rope as a whole. So that now it's like this little system in green that I drew above. And again, saying that the direction it moves is the positive direction. So let's go ahead and label what forces are positive, what are negative. And again, just all the forces in the direction of the rope are considered the x direction. Okay, so Fg, the system is moving that direction, so that is the positive direction. Tension, that is going opposite the direction it moves, so that's going to be negative direction. Okay, let's look up here. This tension force right here, that is along the direction of the rope, so that's our x direction in this case, and it's moving that direction, so that's positive. Friction is going opposite that direction, so that's negative. Fn and Fg, those forces are perpendicular to the rope, so those are like our y direction. So when we're looking at the acceleration of the system, it's only accelerating in the x. It's not accelerating in this y direction, so we'll essentially get to ignore that y direction, which is kind of fun. Okay, so after we go ahead and do that, Now we're going to set up FNet in the x direction for each object. So let's go ahead and do it for the 8 kilogram first. So for the 8 kilogram, let's look. We have FNet x is equal to what forces are acting on it in the x direction. Let's see, we have tension pulling to the right, take away FF pulling to the left. So we have FNet is what? Mass times acceleration. So that is going to be 8 times A equals tension minus 16. Cool. And I should include FNet as MA. That was lazy that I didn't write that. Cool. So I'm going to go ahead and leave it like that. I don't know tension. I don't know A. Let's come back to that. Okay. So now let's look at another object. Let's look at this 10 kilogram. Okay. So we have FNet, okay, is equal to, we have gravity, which we said was the positive direction, tension, which we said was the opposite direction. So FNet is mass times acceleration, which we know is 10A equals FG is 100 pulling down minus tension. Then we have 100 minus tension. Cool. So now we have 2 equations and 2 unknowns. So there's multiple ways to solve this. I want you to think of some ways you know in math to solve it. Okay, so a couple different ways. One thing could be substitution. You could solve for, let's say, t here and plug it into here and then solve for a. One method I love, just because I feel like it's just always so simple and straightforward, is elimination. So I'm going to go ahead and show elimination on this video. So we have 8a equals what? T minus 16. And then we have 10a equals 100 minus t. And I'm going to go ahead and essentially add these 2 equations together. So we have 8a plus 10a, that's going to be 18a. Okay, we have a positive t here and a negative t here. Oh my goodness, and it's just one of each. Cancel, cancel. So fun when things cancel. We have 100 minus 16, which is 84. Cool. We can do some handy dandy math, and I get the acceleration to be 4.67 meters per second squared. Awesome. Any questions on that? Well, I guess you can't ask a question. You can type it in the video chat. Okay, so now, okay, for B, it wants us to find the tension in the string. So thinking about this earlier, if it's accelerating downwards, so Fg is 100, so I know Fg has to be bigger than the tension force because it's accelerating downwards. So that tension has to be less taut than 100 newtons. So let's see if the math proves it. Let's go ahead and plug this in. You could pick either equation and you should get the same thing. So it'd be 10 times what? 4.67 equals 100 minus t. Oh, I love multiplying by 10. It's so much easier. 100 minus t. And then we do some good old math. Take away 100 from both sides. The negatives cancel out. And I get, well, 53.3 newtons. Awesome. Thanks for watching.